Hi, I'm Ramsey Faragher. I'm a Bi-Fellow of Queen's College, Cambridge. I'm the CEO of Focal Point Positioning. Top Gear magazine once labelled me the real-life Q, and I'm going to be talking today about GPS. So, on today's first Bad Boy Meets, we're talking to Ramsey Faragher. Ramsey, it's very good to have you.
Faragher.
You've only known me for...
I've only known you for how long?
Years.
Do you know who I am?
Probably more than 10 years. Ramsey Faragher. The G's hard.
I've always said Faragher.
And I've always...
Why have you never corrected me? Why has he never corrected me? The mysteries of science.
That's the Irish pronunciation, but I'm from the Isle of Man.
We're from the Isle of Man.
We should probably not dwell on
So
this.
is this cultural appropriation? Or
we might just want to restart, but it's Ramsey Faragher.
No, I'm happy with that.
A few moments later.
Hi, I'm Ramsey Faragher. I'm a Bi-Fellow of Queen's College in Cambridge, and I'll start again.
Well, we're from Ramsey Faragher.
We nailed it!
Ramsey is an expert in navigation, tracking and sensor fusion. Essentially, if you want to know where something is and what it's doing using technology, he's your man. So much so that Top Gear magazine described him as a modern Q from James Bond. So today, he's the focus of our first Bad Boy Meets, Ramsey Faragher. The G is hard.
D is sound here, baby.
He was also, as he's alluded to in our introduction here, my first 1A lab supervisor. So picture the scene.
Your audience might know what 1A means.
Well, 1A is the first year of Cambridge. So here in Cambridge, 1A, first year, 1B, second year, part 2, third year. So picture this, a young lad, 19 years of age, comes down from Leeds, full of hope, full of wonder, enjoying Cambridge, done well in his exams, first lab, do the report, comes back. 1 out of 4?
1 out of 5.
1 out of 5? And what had I done wrong? I can't.
It was just...
You remember the talk, right?
I remember giving you the talk when I saw you.
The talk?
Yeah, sort of saying, you're currently down here and I need you to be up here.
Well, I like that his hand was actually like below the table, like off the camera. It was, yeah, and it was that low.
You did get better. You just...
You did get better.
You just hadn't put as much effort in as sort of the next rubbish person in the class. But you picked yourself up and, you know, particle physicist from CERN, PhD. The boy done good.
So Ramsey gave me the kick up the arse I think that I needed at the start of Cambridge, which I very much thank him for, but it was a bit rough at the time. So he destroyed me in that first report, and the next time I saw you, the second time I saw you actually, was you trundling around the Cavendish being our laboratories here at Cambridge University for physics, with an antenna in a backpack.
Probably, you're strapped to a big trolley.
What was the deal with that?
My PhD was working out where you are using mobile phone signals and finding out why the accuracy was poor for the methods people were using at the time. And I studied why the performance was so bad and made it better. And that's how my career started. I thought I was going to be a astrophysicist looking for extrasolar planets.
I want to be an astronaut.
But I decided I was going to make the blue dot on everyone's smartphone better instead. Thought it might be a more useful thing to do.
Blue dot, kind of Carl Sagan-esque though, I guess we can segue into a bit of that. So, to give Ramsey a fair introduction, again, he's an expert in navigation, tracking and sensor fusion. He's a fellow of the Royal Institute of Navigation. He's a chartered physicist, which I didn't realise there even was that outside of accountants.
You can become a chartered physicist in the Institute of Physics. You're supposed to keep paying more money afterwards as well.
Okay, good.
To maintain your chartership.
So you pay rather than it allowing you
a little bit more than non-chartered physicists.
Okay, but what do you get with that?
I get to put CPhys on my CV.
Does that help a lot?
Next question.
Fine. He's a former principal scientist at BAE Systems. a By Fellow of Queen's College, Cambridge as well, where we are now. Beautiful Queen's College. And he's the CEO and the CTO and founder of Focal Point Positioning. So anything to do with tracking, sensing, navigation, networks, Ramsey's your man. And he's someone who point blank refuses to talk to me if I'm on Starbucks Wi-Fi. Now, why is this?
I'm not even sure what you're referring to. Did I refuse to speak to you?
You refused to speak to me when I was on Starbucks Wi-Fi. And I cannot for the life of me remember why.
Probably just based on the fact that it's probably very insecure and whatever was coming off your laptop might not have been.
I thought you might have been, but I thought you might have been
to.
tracking me or using something a bit more in depth than that. But maybe you were just winging it, or probably just didn't want to talk to me. To be fair,
it could have been that as well. There's generally a few excuses I give you over Facebook when I just need to get off.
Ramsey has 2 young children as well, so when I'm looking to pick his brains on something technologically or scientific, he has various escape routes that.
I did have those children just so I'd have more reasons to get off the phone to you.
Fair enough. One other thing that you actually taught me last time we spoke, little trick, well, we're talking about this. I had a real problem with 3 mobile signals in Cambridge.
You've got many more real problems.
Yes, I do have many more problems.
Go on.
With 3 mobile signals in Cambridge.
Yes.
To which you suggested a potential solution sometimes might be to shape the phone. Talk me through why.
So this actually is something that I spotted during my PhD and has gone on to be like one of the things that my company makes use of now, which is that motion, for a radio system, motion can actually be a very important part of making the radio work better. And actually, the point I raised for you was that if you're ever sort of down in the basement of a building or somewhere deep inside a building and you've hardly got any mobile phone signal and you can't get a text to go, what you might find is if you press send and then move the phone around, the text will go. And that's because you're averaging through the multipath fading. And there's basically lots of little dead spots in the room and lots of hot spots in the room. And if you happen to be holding your phone in a dead spot, then you won't get a signal off.
Yeah.
Therefore, the wavelength is so small that just moving like this averages
Is enough to move over several different phases of the.
And it works. And the changes that my company is making to GPS receiver design is based on this, exploiting motion to make the radio work better.
And this is something we're definitely going to come on to later. So, one other thing. So, incredible resume, incredible amount of work, and interesting work that he's working on at the moment, which we're going to come on to. One thing I wanted to touch on before we leave this introduction was the Top Gear stuff.
Right.
So, being called a real world James Bond Q. So, how did that come about? And what's the deal? Are you out there keeping us safe from the terrorists and Daniel Craig's spectres of this world?
No. But like everything that Top Gear does, it was a great story, wasn't it?
It was good.
Connected to the truth.
Was this back in the Jeremy Clarkson day, or was this?
Yes. So basically, the Skyfall movie was coming out, and we had at BA Systems unveiled this technology I developed called NavSop, which used mobile phone signals, television signals, any opportunistic radio signal of any type to augment or replace GPS.
Okay.
So we'd unveiled that, and there'd been some press on it. And Top Gear magazine wanted to do.
So is this for use when GPS isn't available, or is it an alternative to it? Or
exactly, you can combine GPS with opportunistic signals to get better performance in some places. Yeah. But if GPS has gone down, then you rely on stuff that's still there.
Yes.
And there's opportunistic positioning on your phone all the time. Your phone uses Wi-Fi and cellular positioning when GPS isn't available right now today. And when Top Gear came and interviewed me and discussed more and more about all of the stuff I'd actually done during my career to that point, they found that I'd worked on stuff to do with nuclear submarines, Martian rovers, drones, soldier tracking technologies. I'd had the opportunity to work on a whole massive range of different things. In fact, I've never met another person who's worked on both the navigation system of a Martian rover and of a nuclear submarine. So I might be unique in that respect.
Amazing.
But when that all came out in the interview, the interview kind of moved away from a piece on NASA to a piece on someone who does loads and loads of different things. And I mean, yes, they decided.
Which you didn't mind at all.
I was a bit confused when they told me specifically to wear a brown jumper and a blue tie for the photo shoot. But it turns out that the publicity for Skyfall, the young Q, is wearing that.
Yeah, we're going to get into this picture of you in a second. So, this picture, I thought they basically said to you, dress like a Cambridge professor. To which, we'll put this up on the screen in the video, obviously. To which this was your comeback, which I thought was I thought it was pretty.
They told me exactly what to wear.
/ geography teacher / public menace.
I had to buy a brown jumper.
Did you actually?
Yeah.
So you played the part, but to me, you look more like a Bond villain here than Q. So I mean, look at the finger position. Look at the general menace and smirk in the
I
face.
think I'm holding a screwdriver and some kind of development board or something.
Oh, is that what it is?
Probably.
I thought it was where we're going to send the missiles. But you've also got this thing that happens with every James Bond villain, where they seem to have this sort of generic neural network nodes and pathways thing behind.
So, again,
it's like, where are we going to send the missiles
Top Gear
tomorrow?
team just did that. They brought that stuff to put in the background of the photo shoot.
And just a load of like random tabs that people have opened with like things going on that just show, you know, how the revolution will come about. But okay, so they forced you into this position, really.
It was a whole day of taking photographs of me in various places. The most gutting thing was that they said at the end of the day, it's a shame we couldn't bring the DB5 for you to sit in, but it's raining. So
that is pretty upsetting.
Trump style, the fact that there was a bit of rain. they didn't let me drive an Aston Martin around the ground.
But that's one of those things where you like, just don't tell me that.
Yeah.
No, just why have you told me that?
Yeah.
It's like saying we were going to do Christmas, but we're not going to bother because it's raining a bit. So moving swiftly on for that. So give us and give the viewers out there a bit of a feel for your current specialisation. So we talked a bit about the Q stuff. What's your company doing nowadays to save the globe and bring around world peace?
So Focal Point is a company that provides software upgrades to other people's technology.
Yeah.
And the most exciting thing we're doing is changing the software that drives how a GPS receiver works.
Okay.
So we change the code on other people's GPS chips.
So just to cut in, sorry to cut you off, we're going to come on to exactly how GPS works, the technological setup and why it's important, but please, sorry to cut you off there.
That is fine. So we change the code on other people's chips so that it's using our new method.
Yeah.
Because GPS receiver design hasn't changed in decades, really. And so we change how it works, and it increases the sensitivity and the accuracy. And for the first time, with Focal Point's technology, a GPS receiver can determine whether a signal is truly coming from the satellite or whether it's coming from a different direction.
Okay.
And we can actually image that information as well. So
that's a big problem with current GPS. That seems like a very big fault.
Yes, well, it's the reason why GPS behaves badly in cities.
Okay.
So you can be in an urban canyon, so you're in an environment with very tall buildings either side of you, and the GPS signal can bounce between the buildings and come to your receiver after many bounces.
So you essentially get sort of virtual image of where the thing, like if you look in a mirror, the light is not actually coming from behind the mirror.
Yeah.
You're getting that virtual image of where the thing potentially came from, which
indeed.
Kind of seems like the sort of thing you're talking about with the GPS signal.
So a simple example is you can be driving along and you've got buildings in the way with streets between them and a low satellite there. And as you drive along, every time there's a gap in the buildings, you actually see the satellite.
Yeah.
And when there's buildings in the way, the straight line path is blocked, but that signal can diffract over that building, bounce off the nice metal building on this side, and come at your receiver from the other side.
Yeah.
And
so you're getting this. It looks like it's kind of swapping.
Yeah.
The side in which
what that means is that a normal receiver, which just hoovers all of that information up all the time, sees the correct time of flight, and then it sees an extra time of flight.
Yes.
And it just shoves that in the maths, and you get an error in your position. And then when the building is not out of the way, you get the true measurement again, and you snap back. And this is not a known problem. It's just that the methods people have tried to use before to solve it haven't worked very well.
So presumably on your mobile phone, that shows you jumping all over London, by a few extra meters or a street across because of that extra.
Yes, the extra path length of the signal bouncing off the building manifests as pushing you by that extra amount. And the fewer signals you have, then the worse this problem is. So as long as you've got lots and lots of signals, then it's less of a problem.
Because you can throw out that potential.
You have
rogue
ways
signal.
of scoring and throwing away stuff you don't like.
Yeah.
But when you're in a very dense, difficult environment, like downtown San Francisco, downtown New York, Canary Wharf, then you don't have very many signals to play with, and normal GPS positioning will get it wrong, and our algorithms get it right.
So Focal Point very much focused on, or at least one of the big focuses on, improving the quality and the accuracy of GPS systems.
Yeah, by fundamentally changing how the receiver works.
Yeah.
So it's a new step change. It's a new technology, really, that we put on the chips.
Copyrighted, I assume?
It's all patented and
good.
Yeah.
Excellent.
And so that's our GPS technology. We have another technology which is sensor fusion, which sits higher up in any system. So it combines the GPS data, whether it's our SGPS data or a traditional one, with the other sensors that are on the platform and any motion models you have with the platform. So we're also doing stuff at the moment with sports fitness providers, where we provide a much better sports fitness tracking solution than exists today. So if you just use a GPS watch, or you just use a fitness tracker that counts steps and things like that, the estimate of how far you've gone can be really bad. It can be out by like 20%. And our algorithms ensure that you stay at the sort of 1% error type level.
By using other signals that are out there in the world.
Using combinations of sensor fusion and human motion modelling. And because we understand all the ways that an existing GPS receiver can get it wrong, we actually bake that knowledge in of how and when it's likely for the GPS to actually be lying to us.
So it becomes as like a prior in the calculation that goes forward, or your knowledge of GPS. So moving into GPS, it has become very hot at the moment, especially with Brexit and the idea that the UK is not going to have access to Galileo, which is the EU's platform. So
just to a particular part of Galileo. So
okay. Yes. So perhaps it's more nuanced than the Guardian has led me to believe, which is usually the case with the Guardian, to be fair.
There are 4 constellations: GPS, Galileo. I shouldn't count my fingers. There are 4 constellations: GPS, Galileo, Beidou, which is the Chinese one, and GLONASS. And in all of these instances, there's signals that are available for anyone to use, and there are signals that are encrypted and reserved for special use, typically military use.
Yes.
The fuss about leaving Brexit is that while everyone all over the world will use Galileo's free signals, the PRS, the Public Regulated Service, is the encrypted, special, higher performing, can't be spoofed military, basically.
Yes. For intelligence purposes, essentially, and something that security purposes.
It's a more secure version of the signal. So when we leave, we won't have access to use it straight away. Other countries like Norway and America are negotiating access to be able to use PRS, so in other words, to have the keys to the encryption systems.
Which we could potentially do as well, but we wouldn't have immediately.
Wouldn't have it immediately. Everyone else has been trying for more than 2 years and still hasn't got it yet. But the key thing is that the UK has actually been part of the pioneering direction of how PRS has been developed and how it would evolve. In other words, there's a mixture of experts from all over the place, but there is a core of UK expertise and UK production that has been involved in actually making the PRS technology. And we will definitely not be allowed to be involved in that anymore. So we will no longer have a say in what PRS version 2 and PRS version 3 would be. And that has also obviously frustrated us.
I hadn't realised actually that there were so many of these constellations, and there's now been talk, obviously, which I believe you are definitely aware of. I don't know how involved you are with it, of the UK setting up its own system, setting up its own task force at least already, to set up its own GPS system, given the problems of Brexit, which is called...
So the UK Space Agency have not announced what it's going to be called yet. Lots of people have been putting names.
You said he wouldn't tell me the name. So that was a little trick. I was trying to catch him off guard there, especially with half a beer down, to try and get him to just sort of let it out, which he still hasn't.
So, well, the fact is that inside the UK Space Agency, they're still debating what the names might be.
Is it Newton?
I proposed Newton to them. I proposed Faragher to them. Fingers crossed. But
Hawking, he died recently. Hawking.
all of these things are things that people have proposed.
Lovelace for the diversity aspect.
Name a British scientist, and someone has suggested
All
that
right,
it could be. My American friends gleefully call it Brexit.
I do like that. That would. Yeah, that'll work.
We don't know what it's going to be called yet, and even whatever name.
I was looking for a scoop today. We didn't quite get it, but we got the general idea.
Whatever name the UK Space Agency start using for it, I imagine wouldn't be the final name. It's obviously such a big deal to develop a system like this and be one of the 5 GNSS constellations that I imagine the politicians will decide exactly what they want it to be called and why when the time comes to announce it.
What's your feeling? I'm not exactly sure how much you can talk about or how much you are involved with this, as to where we will go with that. Is it likely that we'll negotiate access to those secure signals with Galileo? I know this is something that Brian Cox is always whinging around on his Twitter. Or do you think we're going to go down this route of having a UK specific system? And in that case, would that lead to us having to push our own satellites into orbit to actually set up that system?
So it's all so early days, no one really knows, so I can't give you any scoops because there isn't any knowledge yet.
Sure.
The UK Space Agency has just started a study into some of the early questions. There's a key question like, how will we launch them? We don't have our own launch capability. So obviously they're going around all of the options.
Some guy in a back garden in Bedfordshire. Yeah.
Well, there's various options, obviously. So there's going to be teams going out at the moment to try and find out what the negotiated price might be for launching with various entities and so on. So much of it's so early days.
Yeah.
What I can offer with my confident view, my knowledge of what the UK can do. So Surrey Satellite Solutions builds the Galileo satellites. So we have people and facilities in the UK that can build something that is exactly like a Galileo satellite. So that's easy.
Yeah.
Other people launch.
So we have the technology basically.
We have the expertise. We know how it's done.
Yeah.
We know how much it's cost other entities to do certain things.
Yeah.
We have visibility on whether we think money was wasted in certain areas. There's key parts. The atomic clocks that go on board the satellites are very, very important.
Yeah.
The atomic clocks in Galileo, on the Galileo satellites, are all dying faster than they should be.
We're going to come on to the physics of GPS in a second, because it is a far more involved set of physics than you might initially think.
It's one of the wonders of the modern world, easily GPS. But yeah, so there's all of these parts of the system. How would we launch it? How much might it cost? Where will we get the atomic clocks from? Because get that wrong and the whole system is a failure. So do we try and build our own, or do we go buy someone else's space qualified atomic clocks? All of those questions are being asked right now.
Yeah.
The most important one would be the budget, right? There's an amount of money that the UK would be putting in every year to Galileo anyway, being in the EU.
Yeah.
We will not be putting that money in.
Yeah.
So there's a chunk of money that was already scheduled every year to be put towards a global navigation satellite system.
So it might be just we're set back in temporarily rather than...
Well, the work at the moment will be around, given that that's the current budget, how much more would we be popping into that to do our own system?
Yeah.
And there's always efficiencies that come with being a smaller nation, a smaller group of people trying to achieve a goal without huge amounts of bureaucracy and arguments.
Yeah.
I mean, don't forget, Galileo is very, very, very late. Galileo was supposed to have been launched and fully working 10 years earlier than it's going to be. So a big part of, when you just look at the cost of Galileo, for example, is huge overruns and issues with people arguing.
Bickering between the different nations.
So it's plausible, it's possible, the UK can do it, we've got the capability and the expertise. And so the UK Space Agency...
And Ramsey's happy to be involved, obviously.
Well, the fact is that... anyone who's British and has expertise in this area will at some point be tapped up, I'm sure, to give their thoughts and their opinion on what they know about what could be done better and things like that. So there's not that, we're a small nation, there's not actually that many GNSS experts in the UK compared to in the world.
Yeah, that's a fair point as well. So getting more into the sort of science and the physics of GPS. So we talked a little bit about it, but exactly how does that system function and how is it set up? What's the basic nuts and bolts of what's going on out there in space and how that links to how I get an Uber in Cambridge in half an hour?
I shall try and give you the most succinct description. So GPS and the other technologies, I'll just use GPS casually when I mean GNSS, Global Navigation Satellite System, any of them, but I'll just casually use GPS all the
So
time.
GPS is the American system, just to be. So we're kind of using it, I guess, like Hoover for vacuum cleaner, but
Exactly.
yeah.
So bear with us while we're lazy in our language.
Yeah.
So it's fundamentally it's an orbiting set of atomic clocks. Those atomic clocks all tell the time, and because the speed of light is constant, wherever you are on the Earth, you've got this system of clocks that are all at the same time going tick and sending time.
Yeah.
And that signal of the current timestamp is propagating to everybody all over the place. And wherever people are, they're collecting this pattern of signals from the different satellites. And when you look at that pattern, different satellites, the arrival time of that timestamp has different time arrivals for different satellites. That's it.
So it allows you to triangulate on the ground exactly where you are relative to those satellites that are in orbit.
Yeah, you can basically say satellite 4 arrived first, and then this many milliseconds later satellite 9 arrived, and then this many seconds later, and so on. And the pattern of arrival times of the signals from all the satellites reveals where you're on the Earth. So you do it through trilateration, you do it through least-squares fitting, you slap Kalman filters in there to smooth it all out. Fundamentally, all that's going on is that a receiver is collecting this pattern of timing measurements and figuring out the only place on the Earth it can be.
So it's all those intersections. Where do all those intersections come together to make that position on the Earth, those number of flight times? So that feeds into what you were saying before about the more satellites we have access to, or the more signals we have access to, obviously the error on that measurement of where you are is going to be smaller and smaller. Silly question, outside of Uber and Google Maps, which obviously I use all the time, why do we need this? Are there other uses that we have for GPS? And obviously this is a leading question, because there must be, that we use on a daily basis, which we're not potentially as aware of.
Yes. So it's something like €800 billion of the European economy that's dependent on GNSS in one way or another at the moment.
Wow.
It's hard to actually count all of the ways that these satellite signals help make the world a better place. So, for example, to pick on obvious ones like transport, there'll be millions of people who are alive today thanks to sat-navs that would be dead otherwise because their ambulances would have been in traffic jams. They were rerouted around because of the combination of satellite positioning and things like Google Maps to give you live updates. And the cost of just moving stuff around the Earth and getting things to places on time and efficiently is much easier with GPS. An extreme example I can give you is the electricity that's currently lighting this room is cheaper because of GPS than it would be without, because the substations are all synchronized through GPS timing, and that enables the national grid to be more efficient. So GPS doesn't just tell you where you are to within a few meters, it also tells you a global time to within a few nanoseconds.
Yes.
It can synchronize things around the planet much more cheaply and easily than other methods. And GPS has had loads of extra uses that no one ever thought possible. And we bleed every little last drop out of GPS performance in ways that it was never designed for as well. So to take GPS itself, the civilian signal that we all use has a sort of fundamental accuracy of about 300 meters. And then there's some clever things in the receiver design to sort of find the very leading edge of the arriving signal, so that instead of this mush that's a 300 meter mush, it just finds like the leading edge of this mush to within a few meters.
Really?
And that's why our positioning is a few meters in open conditions, even though the fundamental kind of gifted performance to civilians when the system was designed was going to be much poorer than
I was going to touch on that. So I never thought whether it was an urban myth or whether it was actually the history of this. I was always told that it was limited to a certain accuracy. I think tens of meters, perhaps the 300 meters that you were talking about, and the purpose of that was to stop it being potentially strapped onto some sort of missile or some sort of bomb.
So this was
having that accuracy available to civilians or potentially terrorists.
Sure. So this was called selective availability, and it was turned off in 2000, and it was an intentional dithering of the civilian signal. So instead of just adding white noise, which could be averaged away, there was a not predictive wander of the clock.
Okay.
So that there was this wander in position estimate as well.
In the civilian system.
For the civilian
system,
part.
yeah.
And they turned that off for a variety of reasons. One of the reasons was that actually when Gulf War II, I think it was it? Happened in the mid-90s. Would that be Gulf? No, that'd be Gulf War One, wouldn't it?
Yeah.
So when the first Gulf War happened in the mid-90s, it turned out, as all of the GPS-enabled forces went into that part of the world to fight, that actually they had a lot more civilian GPS kit than military-grade GPS kit with them for a variety of reasons. So at the moment when they would normally ramp up selective availability and make sure that none of the opposing forces were using GPS against them, they couldn't, because
they needed
vastly large numbers of their own forces were using the civilian technologies too. The gear was just much cheaper and easier to get hold of, and easier for everyone to have a civilian device than a military.
So the potential downsides were outweighed by the positives of allowing them to use that civilian signal with greater accuracy, essentially.
Yeah, so coming back to exactly how we can make GPS better in all sorts of ways that we'd never originally thought of, selective availability became useless anyway, because the sort of academic area and the very high precision agricultural and mining and surveying people had already realised you could do some clever tricks to make GPS much more accurate than planned by having a static device somewhere near you, and you only need to be within a few kilometres, gathering the same satellite data as you, and you know exactly where this one is, and you actually transmit to the moving thing the signals that it's picking up and exactly where it is.
So you can filter out the error that's been added in and get rid of it.
You're just minusing out the common errors.
Yeah.
The selective availability is a common error. Both are seeing it, so it minuses out.
Yeah.
So this technique, called differential GPS, has been used in its most extreme form when you use the carrier wave signal, which is 20 centimetres long, instead of the code phase signal, which is 300 metres long, as I mentioned before. If you do carrier phase positioning and you use differential corrections, then you can do millimetre and centimetre level GPS positioning, and the difference between those two is just how expensive your antennas are and how much averaging you do.
So even with that fundamental signal being set to be 300 metres or whatever, you can get around it so much to get millimetre level precision, even with civilian devices.
Yeah. So getting rid of selective availability just meant having another receiver and a mobile phone connection or a radio connection.
Wow.
So they might as well turn it off, right?
Fair enough.
So they did.
So it was pointless. So essentially, in the end, the downsides of keeping it off had been overcome by the upsides of just allowing the US military, for example, to use civilian devices. And
by turning selective availability off, the impact on the economy was huge.
Yeah.
So this is why so much stuff today is now dependent on GPS, because GPS is accurate in a few metres in position and a few nanoseconds in time. And
what is the fundamental accuracy now then of the civilian signal, without any sort of special tricks? And
so the laziest, dirtiest, quickest thing you can do, if you coded up your own GPS receiver, you'd be getting a position fix of about 100 metres, and then it doesn't take too long to add a few more bits and pieces to get you down to tens of metres. But then to really get down to sort of metre level with civilian stuff, then you need to make sure you've done all the relativistic corrections, and you need to make sure you know what the ionosphere is doing and the troposphere, and you have to build in all of the extra complicated bits and pieces of the hard physics that get in the way when you no longer just pretend the signal moved in a vacuum.
I was going to talk about this. So it sounds very easy. We fire these. Obviously, it costs a lot of money, and it's not as easy as that. Just put some atomic clocks in space, crack on, and we're done. And then we do some time of flight calculations. You know, distance equals velocity times time. Speed equals distance over time, and we're done. Obviously, it's not that simple. We've got to get the satellites up there and working. And what are some of those harder physics problems that you talked about? So we're talking about relativity, both special and general, I guess, is coming in. We're getting things flying around at great speed, so there's a special, and also we're talking about gravitational differences between the ground and where these satellites sit. So I guess we've got some quite complicated physics that comes in there, particularly if we want extremely accurate measurements on the ground.
Yes, the global navigation satellite systems are all good examples of tests of of Einstein's equations. So the satellites are about 20,200 kilometers away, and they move at about 4 kilometers per second. So if you didn't account for special relativity, you'd be losing something like 7 microseconds a day or something of the getting out of sequence with atomic clocks on the ground and in the sky.
What would that translate to in, just thinking about
so a microsecond is 300 meters of error.
Yeah.
So you're getting on for kilometers of error.
Yeah. So huge problems if you weren't to take into account the special
it would stop
relativistic
working.
It basically
launch
would be
it, press
unusable.
go, and the next day wouldn't be working. The general relativistic corrections are even greater. That's 30 odd microseconds, I believe, a day. So yeah, the effect of the atomic clocks being in a weaker gravitational field when they're up in space means that we actually set them differently on the ground. So the atomic clocks, if you collected them all together on the ground before launch, the ones you were going to keep here and the ones you were going to send away, they'll get set to 10.23 megahertz as their sort of core tick. And then what they do is they take the ones that go into space and they dial them a little down to, I'm shamelessly going to read it because I can't remember it, 10.2299999543, and I may have missed a 9, but I'm sure you can put it on screen.
So that tiny correction
Dial it
allows,
slightly down, and then when they put the satellites in orbit and we gather these ticks from the sky and compare them with our atomic clocks, their brothers and sisters on the ground, everything is ticking at the same rate.
So as you say, it's also an incredibly sensitive and incredibly accurate experiment that verifies Einstein's predictions of these phenomena.
When they put the test satellite up for GPS, there was debate about whether special relativity was real or whether it was just a trick of maths or whether it was illusions. And maybe it sort of happens, but it doesn't physically happen. Like the clock will actually be ticking the right rate if we bring it back down again, and so on. And they put all these corrections in and just put a switch so they could toggle it on and off, so that if they could make the decision in orbit.
So the Einstein is right, Einstein is wrong switch.
There's literally a lever labelled like that in the satellite, the first test satellite, and sure enough, they needed to turn on all of the relativistic corrections for the satellite to be broadcasting as desired.
Because otherwise, in a day, it would be literally
you'd have put up a clock that was ticking at the wrong rate. Yeah.
So this is a very complicated system. There's lots of things that can go wrong. Lots of things we have to think about. What are some of the other things that make it difficult to get high accuracy on the ground with position? And I remember you mentioning before we started that in the early stages of GPS, you had to kind of warm it up. You couldn't get an accurate position measurement when we started.
Yeah.
What was that related to?
So what I was referring to there was how today we can combine GPS information with other technologies and make it better.
Yeah.
For example, the fact that GPS is now built into our smartphones, specifically the mobile phone connection, can greatly help the GPS receiver in a bunch of ways. The easiest and most important way is the speed it takes for the time it takes for the GPS receiver to actually get a lock when you first turn it on.
Yeah.
So 15 years ago, if you bought a sat nav and you plopped it on the windscreen of your car, you would wait 2 or 3 minutes before you got a fix and could drive anywhere.
Yeah.
And that's because the receiver's downloading data from the satellites.
Which I guess even has economic implications if you're a delivery driver who needs to go somewhere and you're losing 3 minutes every time you need to do a delivery, this is a huge improvement.
Yeah, and time to first fix is one of the scores of how good a receiver is. Sensitivity, accuracy, all of these things. Time to first fix is one of them. And so without the assistance of the orbital data being sent over the mobile phone network instead, you have to download the orbital data from the satellite itself, and this is a satellite that's very far away, very, very weak, and it has 50 bits per second transmit rate, which is pathetic. So it takes a long time.
It's like Napster level when we used to get I'm old enough. I'm old enough to remember the screeching.
50 bits per second is much worse than dial-up. So basically, you can send the orbital information that a GPS receiver needs to get going over a text message like that, instead of waiting 18 to 30 seconds for it to come from the satellite. So that was a big improvement straight away. So you turn on your phone, you just open Google Maps or similar, and the blue dot's there straight away. And it's because the time it's taken for the app to come up the servers go on bang and given you all of the orbital data you need over the mobile phone network and hot started your GPS receiver. Otherwise, it needs to listen to the satellites for it doesn't listen for where they are. It listens for about a dozen or 2 dozen orbital parameters for the Keplerian orbits and corrections and the clock corrections.
Because it has to know exactly where those satellites are.
So when it picks up this timestamp from the satellite, it then uses that timestamp to work out where the satellite was.
Yeah. And
then you go through an iterative process where you solve the whole system. Where must it have been in order for the time to have been where I picked it up now and so on. But you need to know where the satellites are.
So what are some of the other, outside of the hard physics, so we move out of the physics, which obviously is my field, into the sort of the more engineering, I guess, the messy, real life stuff. So in theory, bang them up there, signals come down, hey presto, we know where we are. What are some of the messy things on the ground that you deal with that make getting that millimetre level accuracy on the ground difficult? So I'm thinking about things getting in the way, weather conditions.
Sure. So to get millimetre accuracy, we use the carrier phase itself. So the radio transmission from the satellite is broadcast on a 1.5 gigahertz carrier. So the wavelength is about this long. And the problem is that every wave looks the same. So while you can measure the phase between 0 and 2 pi of where you are along here and do millimetre accuracy, when you're getting these numbers from each satellite telling you, 0.2 radians on that one at the same time as 0.9 radians on that one, and you've got these phase difference measurements, the problem is this signal's coming through the window behind me. If I'm measuring 0.2 radians, that just means I'm either there,
because of the periodicity of the wave.
All the way up to the satellite.
Yeah.
And having this pattern of just a number between 0 and 2 pi on all the satellites gives you a huge number of ambiguities as to where you are. So if you want to use carrier phase positioning and get millimetre level tracking, then you need to have a way of resolving this ambiguity and effectively figuring out where you are first within, say, 20 centimetres, and then you can nail down.
And then you can nail down within that particular wave.
And so the easiest way to do that would be for the code, the data modulations on that carrier to be able on its own to give you an accuracy of already down to 20 centimetres. But what drives that is the bandwidth of the signal. The higher the bandwidth, then the finer you can make this code phase measurement. And normal GPS has a code bandwidth of about 1 megahertz, which just equates to about 300 meters. So you have to go from a 300 meter uncertainty down to 20 centimeters. And there are a bunch of things we do. So one of the first easiest things is you actually have a bit of digital signal processing to just look at the edge of the chip transitions. In effect, it's not quite this, but it's the easiest way to explain it. So in other words, if you imagine you've got a sawtooth pattern that's 300 meters long, then instead of trying to sort of figure out where the middle of the 300 meter sawtooth is, it makes much more sense to go and look at the edge of the sawtooth, right? So you can start trying to pay attention to those things. That gets you a few meters.
So you're treating it sort of like a binary signal. It's either nothing or you're at the edge of that sawtooth.
And in reality, we do what's called narrow correlator spacing, which is trying to do the same sort of thing, drive you towards a finer and finer estimate of where the edge of the chip is. But in terms of real life, trying to go from the code phase measurement to the carrier phase measurement, the biggest problems are multipath interference and non-line of sight, when you've got buildings in the way. And that will always be the big problem with using satellites to work out where we are.
So this is literally just, we have a block of stuff in the way of getting that direct line of sight.
And worse, that signal has probably bounced off something else and still come to us. So life would be great if the satellite's signals were either line of sight or not line of sight. GPS would be trivial, and my company wouldn't need to exist. But in reality, whenever you block a signal, all that happens is the receiver picks up a bunch of other versions of it that have bounced off and come some other way. That's the non-line of sight problem. Then the multipath interference problem is when the line of sight was there, but a delayed echo is coming into the receiver at the same time with only a small path delay. And when two signals come together with only a small difference in delay, then they can interfere in complicated ways and cause huge errors.
So that would suggest that two satellites are a similar distance away from
No, so
position where the
it's
person
that the signal has come through that window to me.
Yeah.
But it's also bounced off this building here a few meters
okay.
away
I
and
see.
come to me.
I see.
So the difference in path length for those two is only a handful of meters.
Yeah.
It's come from the same source, and this was actually what my PhD was looking into, multipath interference, and it's fascinating but true and modelable that you can have two signals that are only delayed by a couple of meters, but if they're completely out of phase, when they interfere, the resulting measurement can be hundreds of
It's
meters.
worse than that 2 meters.
Way worse.
Different. Yeah.
In fact, the worst it can be is half your coherence length. So for GPS, 150 meters. So you can.
So try getting a taxi in New York with
and you might be in the
150,
wrong
but
block.
you might be literally in the wrong, on the wrong street with that.
So one of the most compelling experiments I did during my PhD was I was on the roof of the Cavendish laboratory. I was allowed to be. I think I was allowed to be. I was on the roof of the Cav, and I could see the mobile phone mast on the other side of a farmer's field.
Yeah.
Right there.
Yeah.
And I was moving towards it and away from it, just gathering a really basic baseline.
So
piece of data.
you had direct line of sight with this thing at all points.
And I had a receiver that could measure the time of arrival and an atomic clock, and I was moving forwards and backwards, and it was supposed to be the most trivial baseline test, just to check how the experiment was working. And what happened was, when I looked at the data, there was a point where I'd moved sort of one step, and the apparent distance between me and the mast was hundreds of meters towards the mast. And then I finished my footstep and I was back on the roof.
This is what we call an artifact in physics.
It's what you might call an outlier.
An outlier.
For me,
Yeah.
it's the
You didn't do
entire
anything
crux
wrong, but it just went mental.
the problem.
Yeah. So
Well, that's multipath interference, and that's one of the biggest problems.
So what had happened there? It bounced off a fence or
Yeah, it
some
bounced
other
off some
feature in
object on the roof.
Yeah.
And so I was at a moment where the line of sight signal and a non-line of sight copy that had bounced in and had arrived with a very small delay
off a car or some other building or
probably
something
just
else on the roof.
the door that I'd left open
Yeah.
to the roof. But because it had arrived out of phase, when those two things combined with each other, they produced the worst corrupted overall correlation peak. What you're trying to do is figure out where your correlation peaks are. So a correlation peak is how you determine in time when the signal arrives. You do a process called correlation and you see a peak. And so you look at whether those peaks are arriving earlier or later to determine if you're moving towards or away from something.
Sounds a bit like two
And this peak
young slits
can get
experiment.
corrupted. Yeah, indeed. And so the issue with multipath interference is it corrupts your correlation peaks.
So essentially,
causes
if we
errors.
come completely out of phase, sort of GCSE A-level physics, we essentially don't have a signal. Right? If they interfere incoherently, we're obviously going to lose that quality of signal if we get any signal at all.
Yeah, exactly. And if they'd been the same path length and you'd interfered them perfectly out of phase, it would have completely disappeared.
Yeah.
But because they're ever so slightly offset in time, but out of phase,
You've got the
you get
corruption
sort of
and
maximal carnage.
maximum. So you're still getting the signal. It's just awful.
Yeah.
In a way, you'd probably rather not get the signal and realise that you have that problem.
Yeah.
I can't give you an accurate measurement at this position in space, rather than, I think I can give you a measurement, and here's a load of rubbish that you can't actually deal with.
And this is what the technology that my company's developed now sorts out, because what we do is we exploit the motion of the platform, and we know that given your current motion, a particular pattern of Doppler shifts should occur for signals from different directions. And we intentionally use a very long coherent integration time. So a normal GPS receiver would process, say, 10 milliseconds of data at a time, and that's it.
Yeah.
So even though your position coming out of your phone might be once a second, what's happened is the receiver has made 100 measurements a second and averaged them together.
I see.
And each one used 10 milliseconds of data.
Yeah.
We flip that around and we take 1 second's worth or more of radio data, 100 times more data than normal, right? And we figure out the pattern of Doppler shifts that would have occurred during that time for the motion you're on.
Yes.
And tailor it for the line of sight you're expecting.
Yeah.
And so we can actually separate out for the first time the line of sight stuff and the non-line of sight stuff because of the direction they're coming from relative to the motion we're going. And we're just the next step in the evolution of GPS.
And that's
it's been evolving for decades, and it'll evolve for decades.
That's your contribution to this. That's the patented extra contribution
That's
of focal
the
point.
software upgrade that Focal Point are providing to GPS receiver manufacturers at the moment. Yeah.
Superb. So moving into the final part of today's interview, you popped up on my Facebook feed as you regularly do, or well, not so regularly now actually.
Twins since the twins came.
Yeah, since the twins came. So you can try his own twins paradox. You know, trying to do this interview and juggle the other stuff, but. An article came out from the erstwhile website I Fucking Love Science. I always get everything right, of course. And they said that we've invented a quantum gyroscope that will essentially make GPS obsolete. It will make GPS style measurements, which are 1,000 times more accurate than GPS. And therefore, Mr. Ramsey Faragher, thank you very much for your work in the past, but you need to move on with the times. And this, understandably, upset you a little bit. What's the story there?
So it's not true.
That's a good reason to not be too happy with it.
Let me try and break it down a few notches. So, firstly, the UK is working on a bunch of new quantum technologies. They're calling it Quantum Version 2. Something like £270 million has been spent so far across 4 different hubs inside the UK. There's a sensing hub, a communications hub, an imaging hub, and sensing, computing, communication and imaging.
That's
4
right,
hubs. And so the sensing hub has been developing new sorts of accelerometers and gyroscopes. Very sexy science. Bose-Einstein condensates use lasers to cool a cloud of atoms down to almost nothing. They all start to behave as one wave-like object, and so you can do interferometry with matter waves, and these things will inevitably be much more sensitive and precise than traditional accelerometers and gyroscopes, because the wavelength of Bose-Einstein condensates is much smaller than the wavelength of lasers, which is what we would have used before. So there's all sorts of things in the kind of physics story as well. Surely it's going to be great because it's going to be orders of magnitude more sensitive, but even if you had perfect accelerometers and gyroscopes with no error at all, they would still not render positioning technology.
Which we can never have because of quantum.
Yes.
Right. Physics.
Tick. Mark in the exam.
Yeah, otherwise they'll be marking me 1 out of 5 again. So
just put Heisenberg and surgery.
Yeah, exactly. And
if it's not looking right, there's probably a root 2 missing.
Yeah, there we go.
Exactly. So the most fundamental issue is that even if you've got perfect sensors, that's great from the physics point of view, it sounds exciting, but actually there's some engineering work that then goes on into having a practical system that works in the real world, and all sorts of nasty real world issues get in the way.
So the real world gets in the way of physics as usual,
often.
The beautiful physics.
Or the maths, the easy bit of the maths, the stuff you can derive. So some important areas are just in the fact that we have to use computers to solve for our position using accelerometers and gyroscopes, and you have issues of numbers can't be represented fully in binary, pi can't be represented fully inside a machine. There's linearization aspects, we make approximations all the way along the way. Basically there's all sorts of computational errors that mean that even if you had perfect sensors, your estimate over time of where you are will degrade. But the biggest one by far is the fact that gravity needs to be accounted for. So from the equivalence principle, accelerometers reading 9.81 are either sitting still on the Earth's surface somewhere or are out in free space being accelerated at 9.81.
So we can't tell if the difference in their measurements is coming from their motion, special relativity, or from a difference in local gravitational field, the general relativity.
Yes, so give me a perfect accelerometer that's measuring 9.85, and am I somewhere where the gravity is 9.82 and I'm accelerating at 0.03, or am I somewhere on the Earth's surface where the gravity is 9.85
and I'm sat still?
Because if I just integrate up over these two hypotheses over the course of a day, one of those would stay still and that might be correct, and the other one would have this continual error growth that's just getting
because
worse
I'm
and worse
moving
and worse
away at this acceleration presumably.
So perfect accelerometers and gyroscopes are actually pointless because we do not know what the correct number for gravity is all over the planet. And people move. And
which changes
change,
based
and
on the
volcanoes
local rock composition or on where people are moving, or the fact that that thing is a little bit closer to you.
And if you're trying to send a probe from here to another planet, you've got to take into account all of the planets that are moving and other bodies that are moving and all of that stuff. So,
so it's an impossible calculation to do. So it's a nice thing sort of in theory, but in practice, it's not going to get us away from GPS.
Yeah, so even if these sensors ever hit a point where they would only have 1 metre of drift after a day, well, that just means that after that day, you should definitely go and cross-reference with GPS, because as we discussed earlier, GPS can tell you whether you are to better than a metre. And so...
so what could this be used as a very accurate short-term measurement for certain uses? So, essentially, which then has to be recalibrated with GPS, for example.
We use inertial sensors right now today to bridge gaps in GPS coverage and other positioning technologies coverages. So one of the most likely places that these technologies will end up is in nuclear submarines, so that they don't have to come up as often for fixes. Simple as that. But it doesn't render the technology they use when they come up to get a fix obsolete. The other application I expect they will have is, flip this round, they'll be useful for measuring and mapping out the gravitational field strength of the Earth in various places. And actually that in itself is a very useful thing to do, because that's how you go looking for more oil fields and precious minerals under the ground and do interesting science. So
they're very interesting and useful things, but the idea that the sexy headline that is just going to destroy GPS it's exactly that. It's just a hook for people to click on the website and have a look at what's going on.
And I and others at the Royal Institute of Navigation have been sort of managing this
expectation
over the years of actually holding workshops and having conversations and bringing the physicists in the labs together with the Royal Institute of Navigation and others to make sure they understand that they're not developing a golden bullet, and they need to...
Because I guess the problem... is that they move money out of GPS systems, particularly at a politically fragile point we're at the moment. If everyone just thinks, oh well, thank you, Mr. Faragher, excuse me, we don't need your services anymore, you've done well up to this point, but really you should be moving into quantum gyros, then we're potentially moving in the wrong direction.
It's certainly concerning if people read headlines that said anything could render GPS obsolete, and that was a decision point as to not to continue to try to be part of Galileo or to fund our own UK GNSS based on something that's not true. Critically, it's not even come from the scientists. It's an unfortunate example. I think if you trace the storyline back through, there was a sort of core article where the reporter had decided it was not a very sexy story to say scientists make object in the laboratory smaller and battery powered, or say scientists made an accelerometer that's a bit more sensitive than all the accelerometers we use today, and instead say scientists create quantum compass, which wasn't true because it isn't a north finding device
that destroys a huge piece of modern technology,
renders GPS obsolete, or whatever the wording was. So my beef was with the headline that could convey the wrong message about the technologies at a time when we should be understanding how we spend our money split across these exciting branches of science.
And I think that's a very fair point, because I mean, we're talking about I fucking love science article, but this was picked up by more reputable outlets as well, and it's something that does the rounds, like we were saying before we started the video. It seems to do the rounds every year or 2 years. It just sort of seems to get dragged up by the new staff rider.
So the quantum hubs have an annual kind of report conference thing in London.
I see.
And so every year it comes up.
So that makes sense. But yeah, it's very important to understand that this is not, as you say, a magic bullet that's going to destroy GPS, and we should understand that. So, very final thing today. What is the next big thing in sensing, networking, GPS, focal point? What is the big thing that's going to affect our lives? What's going to come to my mobile phone that is the brainchild of Mr. Ramsey Faragher? And what can when I look in my mobile phone, when I download an app, how can I say Ramsey is making my life better today, as he regularly does.
Well, it's going to sound very arrogant for me to say it, but yes, the technology.
I just asked you a question that
Yes.
was, how are you going to make my life
very
better?
leading
I
question.
allowed you to. Ramsey's not an arrogant man. He's an extremely lovely and.
We are in the middle of an exciting time where we're negotiating the deals to get our technology into smartphone chipsets, so that there'll be a handset in 2020. So in 2020, the little blue dot on your phone will be
On my Google
in
Maps.
cities. Indeed, on any of the technology using your phone, will be much better in cities, and that'll be thanks to us. You may never. Your listeners may never hear from us directly because that's the nature of the beast.
Yeah.
We're simply selling the software to the people you do hear about, the names of various big companies across the world. But yes, hopefully I'll be helping you all get to the shops, and more importantly, help you get to hospital if you need to, or a ambulance man find his way to you if you need him to, and so on, in a few years' time. That's my take on the smartphone side and the GPS side. And in the broader world, although I've just said how the quantum stuff needs to be sort of taken carefully into context, there's no doubt that with the amount of money that's being pumped into those technologies, some really interesting things will come out of it. One of the scariest things we all need to be aware of, and that the UK GNSS constellation builders and thinkers need to be aware of as they plan it all, is that if quantum computing does come along, then it will render all of our current encryption and decryption schemes to be easily attackable. So if anyone is storing now all of your encrypted information that's knocking around on the internet, then in the future they'll be able to read
This
it.
is why you tell me not to use Costa's Wi-Fi.
Probably why I said, well, I can't remember why I was telling you to not to use Starbucks Wi-Fi. But anyway, no offence to anyone from Costas or Starbucks. Other free Wi-Fi that's stealing your data
is available out there. Yeah. But funny story, my friend around the corner, he calls his personal network police surveillance van.
Yes.
Just so nobody dare hack into it. But anyway, please.
One of the most interesting things that might come out of quantum computing is that there'll be this period where a lot of stuff that's currently encrypted but accessible, because people have stolen it from websites, but at least it's encrypted, but they've stolen the encrypted copy, they'll be able to get into it.
Yeah.
So we will need, and there are, before anyone panics, there are flavours of encryption that are robust against the sort of brute force attacks that quantum computers would be able to use on current encryption decryption schemes. But there's an interesting time ahead, I think, in terms of whether quantum computing makes big changes to the world, if it ever comes along.
So focal point will be at the leading edge of all things GPS. And in 2020, if you have a mobile phone and you realise that it's no longer telling you that you're in the middle of a river when you're not, then you might have this man to thank.
You're welcome.
Ramsey, thank you very much for talking to us today. I really, really appreciate it. And hopefully we'll chat again soon.
Cheers, buddy.
Cheers, buddy.